I welcome you all in this session. As we have seen in the earlier classes that we have defined the basic principles of separation processes, definition of the separation processes, and what are the membrane based processes, the difference between the rate governed process and the equilibrium governed process, and we also have seen the categorization of various membrane based processes and what are the typical differences and salient features of each of these processes that we have already seen. Then we have gone through a series of definitions of various terms. Those are quite important during the course of this of this course structure. So, we have already known about the basic terms, those will be appearing in the modeling. Therefore, now we are well equipped to start with the modeling of the various process, and modeling simply means we would like to predict the system performance. And what is the system performance? The system performance is in terms of throughput of the process, that is the permeate flux, and the permeate quality, that is the what is the solute concentration in the permeate. So, these two are the basic indicators of the system performance, because if we can measure or predict the permeate flux quite accurately, that will be helping us tremendously in design of a scaled up version. We will be conducting experiments in a small scale, and then we will be modeling the whole system and compare our computed data with the experimental data. If that matches quite well, then we will say that our modeling is validated. Once we will be using a validated model for scaling up, then we can get the permeate flux in a scaled up version. Once you get a scaled up version of permeate flux, that what is the meter cube per meter square per second, or it is called LMH, liter per meter square hour of flux, then if we have some design in our mind that what is the throughput of the process should be, let us say 500 liter per day or 1000 liter per day or 10,000 liter per day, then we can divide the productivity of this 5000 liter per day divided by permeate flux. That will be giving out the effective filtration area or membrane area. Once we know the membrane area is this much membrane area is required, we can really go for that much of membrane area, or we can procure a model which will be confirming that membrane area. So, that will be very important in scaling up of the process. Similarly, apart from the throughput, for commercial viability, the permeate quality is very important, because in most of the applications we have to confirm the quality of the filtrate or permeate to particular norm. For example, if we would like to have to build up a plant of chromium removal, which will be basically treatment of effluent from coming out from tannery of a leather industry, it contains toxic chromium, and the permissible level of toxic chromium in the in any surface water is around 2 ppm per 2 ppm 2 milligram per liter. So, your concentration of chromium in the filtrate should be less than 2 milligram per liter. So, that whether in your actual system that is really coming out or not, that we have to see. If its concentration is around 5 or 10 milligram per liter in the filtrate, then that is not viable, that is not right. So, the permeate, the process performance is basically indicated by two parameters: throughput, is the permeate flux, and permeate quality or the solute concentration in the permeate. So, if these two are properly done, if you can model this system quite accurately, then we can do away with a number of experiments. So, if we can get in fact this data if we conduct experiments over a wide range of operating conditions, but to conduct so many experiments that will be requiring that they will be investing the manpower, will be investing money, manpower, resources and energy. So, in order to minimize that, we will be conducting very small less number of experiments and confirm our model, and then we can conduct the virtual experiments in terms of the simulation and process modeling. So, there lies the importance of modeling and simulation, and therefore, in order to predict the system performance quite accurately for scaling up of the system of the process. So, first we will be looking into the modeling of an RO system. RO system, and we will be basically do the we will be writing down the transport laws for solute and solvent flow through the membrane per unit time and per unit area. Okay. And these laws are derived from irreversible thermodynamics. Okay. There are couple of assumptions involved. So, let us write down the assumptions involved in the process or in the derivations. First one is flux of ith species is a function of every force existing in the system. Second one is under conditions not far from equilibrium, flux force relationship is linear. So, that means, if we consider that the flux is proportional to the driving force and that relationship is linear if we consider not far from equilibrium. So, we can write that N I, that is the solute flux, is summation of L I j times F j where N I is the molar flux of ith species and F j is jth driving force. And the constant L I j, as we have discussed earlier, it will be the proportionality constant, and that will be nothing but the phenomenological constant. Okay. So, now we use a notation. 1 stands for solute and 2 stand for solvent. So, solvent flux can be written as minus L 2 1 gradient of mu 1 minus L 2 2 gradient of mu 2, because in our system what is the force? It is the gradient of chemical potential. And similarly, we can write solute flux is minus L 1 1 gradient of mu 1 minus L 1 2 gradient of mu 2. Then we have something called Onsager's reciprocating principle. Here we say, if flux and forces are properly selected, for proper selection of flux and force, Lij will be nothing but Lji. Okay. Then comes the concept of coupling. And what is the definition of coupling? Coupling says that due to existence of forces present on another species can influence the transport of a particular species. That means, transport of a species can be dependent on force acting on other species. Okay. So, that is called that is a definition of coupling, and we assume, again we will be having an assumption here, assume that the coupling in reverse osmosis in RO, the coupling is 0. There is no existence of coupling. Therefore, L11, L12 and L21 are equal to 0, and we will be having the expression of solvent flux as minus L22 grad of mu 2 and N1 is equal to minus L11 grad of mu 1. Now, gradient of chemical potential in absence of any electric field, it will be described as in absence of electric field and temperature difference, because most of the membrane separation process are occurring under isothermal conditions. Temperature difference, absence of temperature difference means it is basically isothermal situation. We are dealing with isothermal situation. Okay. So, expression of grad of mu I is written as delta mu I del p constant T and n plus grad of p plus del mu I del C I, okay, constant pressure and temperature gradient of C I. Therefore, we are in a position to write down the solvent flux as, so solvent flux can be written as N2 is equal to minus L22 gradient del mu 1 del p T and n grad of del p plus, so this will be del mu 2. Okay. So, del mu 2 del C 2m pressure, constant pressure temperature gradient of C2m. So, what is C2m? C2m is solvent concentration in membrane phase or in the solid phase, membrane phase. Okay. So, under this we assume again a steady state and one dimensional transport. So, let us write down the system geometry, an axis, this is x equal to L 0 and this is x equal to L, L is the membrane thickness. So, this is nothing but the membrane thickness. C2m prime is solvent concentration of species 2 on the membrane surface in the upstream of the feed site, and C2m double prime is concentration of solute number or solute 2 on the membrane surface in the filtrate or permeate side. Okay. Now, we will be considering a one dimensional and steady state system, and therefore, we can expand this equation. In this equation we can write delta p as dp dx and delta C2m as d C2m dx, and then integrate along the with the dx. So, we can write it as N2 is equal to minus L22 del mu 2 del p constant t and n dp dx plus del mu 2 del C2m constant p and t gradient of okay, we just write d C2m dx. Then we integrate both side over dx and see what you get. So, N2 dx is equal to minus L22 del mu 2 del C2m p constant p and t d C2m plus del mu 2 del p constant n and t dp, and then we integrate across the length of the membrane, thickness of the membrane 0 to L. So, d C2m will be from C2m prime to C2m double prime, C2m double prime, and this will be from P upstream, P are upstream to P downstream. So, P2 to P1, and P2 is the pressure in the feed site, and P1 is permeate pressure. Okay. So, V2 bar, let us define the partial molar volume. That will be del mu I del p at constant t and n. So, using this definition of molar volume, we can integrate this equation and treat at the steady state N2 is constant at the steady state. So, we can write N2 times L is equal to minus L22 C2m prime to C2m double prime del mu 2 del C2m constant p and t d C2m plus del mu 2 del p we can substitute as in terms of the molar volume del mu 2 del p n and t dp, and this will be from P2 to P1. Then we can substitute the definition of partial molar volume by del mu to del p as V2 bar is equal to, and we assume that V2 bar, the partial molar volume, is not a function of pressure over the range P1 to P2. So, we assume that V2 bar solvent partial molar volume of solvent is constant over the partial range over the pressure range P1 to P2 that we are considering. So, once we do that, then we can integrate out the definition of from the definition of the molar volume as V2 bar multiplied by P2 minus P1 is equal to C2m prime to C2m double prime del mu 2 del C2m at constant pressure and temperature times d C2m. Now, this equation is arrived if assuming the equilibrium, osmotic equilibrium. When the osmotic equilibrium is reached, N2 is equal to 0, and in the above expression we can put 0 is equal to minus L2 to C2m prime to C2m double prime del mu 2 del C2m d C2m plus del mu 2 del p. We can substitute it from the using the definition of partial molar volume. So, V 2 bar from P 2 to P 1 that will be treated as constant, because it will be constant over the pressure range times d p. So, once you do that, we get the we do a simplification, we can get this relationship that V 2 bar is P 1 and P 2 when you to the other side, P 2 minus P 1 is equal to C 2 m prime to C 2 m double prime del mu 2 del C 2 m constant pressure and temperature d C 2 m. So, we get this relationship what exactly we have written here, assuming the osmotic equilibrium. In fact, this is the expression of del mu to del C 2 m P and T d C 2 m at the osmotic equilibrium. So, this equation can be treated as a boundary condition of the limit of the governing equation of N2. So, in terms of therefore, in the governing equation of solvent flux, we can substitute this term, the integral C 2 m prime to C 2 m double prime del mu to del C 2 m d C 2 m by this expression V 2 into V 2 bar into P 2 minus P 1. So, if we really do that, then what you will be getting is that N2 L is equal to minus L2 to V 2 bar, and what is this? This, since these will be at osmotic equilibrium, P 2 minus P 1 will be nothing but the delta pi. It will be nothing but the osmotic pressure difference. So, since we are evaluating this term, at the equilibrium condition, the P 2 minus P 1 will be nothing but the osmotic pressure difference across the membrane. So, therefore, we can now write down the equation of governing equation of solvent flux as N 2 L is equal to minus L 2 to V 2 bar times delta pi minus V 2 bar delta d p from P 1 to P 2. So, therefore, this will be minus L 2 to V 2 bar delta pi minus V 2 bar delta p, where delta p is nothing but P 2 minus P 1, or P 2 is the higher pressure. P 2 is the pressure in the feed side, P 1 is the pressure in the filtrate side. So, now we can consume minus sign within the bracket. So, this becomes L 2 to V 2 bar is equal to delta p minus delta pi, and N 2 is equal to L 2 to V 2 bar divided by L delta p minus delta pi. Now, L 2 is a constant, V 2 bar is a constant because it is the molar volume of the solvent. For a particular membrane, thickness is constant. So, the whole thing will become a constant, and this will be nothing but some constant K solvent multiplied by delta p minus delta pi. Now, this is the governing law of solvent transport through the porous membrane, and the unit of N 2 is basically the moles per meter square of membrane area per unit time. Now, this can be converted into gram per meter square per second if we multiply it into the molecular weight, and then if we invoke the term of density, this flux can be written in terms of the volumetric flux. Okay. So, moles per meter square per unit time can be converted into the grams per meter square per unit time by using a factor of molecular weight, and then this can be converted into meter cube per meter square second by using a factor of density. So, therefore, we can really express our volumetric flux as V w is nothing but L p del p minus del pi, where L p is the membrane permeability. So, this gives the transport law of the volumetric flow rate of the solvent through the membrane, and this has a direct bearing of the throughput of the process. Since this expression of permeate flux involves the osmotic pressure and the operating pressure and the permeability of the membrane, this law is known as the osmotic pressure equation, or this is also known as the so called Darcy's law through the porous medium. And since for the solutes having the lower molecular weight, for lower molecular solutes like salts, osmotic pressure is significant, and this is the governing equation of volumetric flow rate through the membrane, and this model is also known as the osmotic pressure model. Okay. So, next, so we have modeled from the irreversible thermodynamics under certain assumptions, we have modeled the volumetric flow rate of the solvent through the porous media. It is basically it is not the flow rate, it is basically the flow permeate flux, and that will be through the osmotic pressure model. Next, what we will be doing, we will be calculating the similar type, we will be doing the similar type of exercise in order to quantify the solute flux through the porous membrane. Okay. Thank you very much.